Okay, let's continue now with the discretization of the convection-diffusion equation. And the first scheme that we are going to look at is the forward time centered space scheme that we have already seen for the diffusion equation where we can use it, and for the convection equation where we cannot because it's unstable. But now we are considering it here for the convection-diffusion equation. As a reminder, the acronym stands for forward time. Okay, in fact, using the explicit Euler method, and centered space. What we do is, if we look in the perspective for the difference molecule, we have the x direction, we have the y direction, then we have a centered node, and that needs information from the two neighbors in the x direction and in the y direction. And this is at the time level n delta t, or Tn. And what we want to determine is the solution at the new time level, that is at the time level n plus 1 delta t. So this is sketched in perspective. If we look now from above, then we will have this situation, that we will have the x direction, the y direction, we will have the center node, and that is then at the time level n. All that we have here is at time level n, and the indices are ij. It is the same indexing as we have been using for the 2D Poisson equation. The right eastern neighbor has then the index I plus 1 j, and the western one has I minus 1j. The northern one has I j plus 1. The southern one has I j minus 1. So that is our usual notation. So that is the difference molecule. And the grid spacing that we have in the x direction, that is delta x, and the grid spacing in the y direction, that is delta y. We assume that they are constant. They can be different, but they are constant. For the discussion, we assume that c is constant. Can easily extend it. For the more general case, then c that we are considering would be then a function, would be at the location xi, yj, and time level tn, if we had more general case. Then the forward time-centered space scheme will be the following. It is now our equation 9. We take the usual time derivative approximation, and now we have the indices ij, the new time level minus the approximation at the old time level divided by the time step delta t. That is our approximation of du dt. And then we have the c1 assumed constant, and the du dx is then approximated by the centered difference approximation. We take it at the old time level, I plus 1 minus I minus 1 divided by 2 delta x. Similarly, centered difference approximation of du dy. Then we have the ui j plus 1 the old time level minus ui j minus 1 at the old time level divided by 2 delta y. So that is the discretization of the linear advection equation by this 4 time-centered space scheme. On the right-hand side, we have the diffusion contribution with the diffusion coefficient alpha, and then we have the second derivative of du dx. So that is then the usual discretization of that is the ui plus 1j. It's the same as for the Poisson equation, but since we are using the forward time scheme, everything is at the time level n. Minus 2 uij and the ui minus 1j divided by delta x squared. So that is the discretization of the second derivative of u with respect to x. Similarly, the second derivative of u with respect to y, that is uij plus 1 n minus 2 uij n. Here I forgot the n. Everything is at the time level n. And we have the uij minus 1n divided by delta y squared. So that is our forward time-centered space scheme. Now let us characterize this scheme. We can get the right-hand side on the left-hand side with a minus. Then we insert the exact solution into that to find the truncation error. And what we find is, and that is classical, Taylor expansion around the grid point xi, yj. The truncation error turns out to be the following. Since we are using the explicit Euler method in time, we have only the first order in time, but since we are using second order central difference approximations, both for the advection and for the diffusion, we have a second order in x and second order in y. So that means this scheme is first order in time and second order in space. That characterizes then the accuracy of the scheme. Okay. For the implementation of this scheme, we will multiply by delta t, and then we will bring everything on the old time level to the right-hand side, that we can compute our solution at the new time level directly. Since we have an explicit scheme, this is very easy. So we get by multiplying by the time step delta t and reordering yields the following. That is 11. That is the way how you would implement it. That we have the solution at our grid point xi, yj at the new time level is equal to the one at the old time level. And then you see here when we multiply delta t, we get c1 delta t divided by delta x half. And that is then the current number in x direction. Here we get c2 delta t divided by delta y half. That is then the current number in y direction is appearing. And since it's on the right hand side, we get a minus. And the current number is again denoted by c. I use now c1 for the one in x direction. And then we have here then the ui plus 1 jn minus the ui minus jn minus now the current number in y direction. And here we have then the uij plus 1 minus the uij minus 1 everything at the time level n. Then we have taken convection or advection into account. And now, regarding the diffusion, when we multiply by delta t, we get alpha delta t divided by delta x squared, that we will denote as the von Neumann number in x direction, and we will get alpha delta t divided by delta y squared, von Neumann number in y direction. So then, let's do that. So we get on the right hand side, in addition, I denote that by R1, the von Neumann number in x direction. And then we adjust this numerator. So it is the ui plus 1jn minus 2uijn plus ui minus 1jn. And we get a contribution also from the y direction. Similarly, uij plus 1n equals 2uijn plus uij minus 1. So that all is then on the right hand side. Now I want to define these current numbers and von Neumann numbers. So what we have used here is that capital C1 is equal to the advection velocity component in x direction C1 times the time step delta t divided by delta x, current number in x direction, and the C2 is correspondingly the C2 delta t divided by delta y. So they are the current numbers in x and y direction. And correspondingly, the R1 and the R2 are the diffusion coefficient alpha and time step divided by delta x squared. The R2 is then alpha delta t divided by delta y squared. That are stability parameters, sometimes called von Neumann numbers in x and y directions. So when we have given these the advection velocity with components C1 and C2, when we have given the diffusion coefficient alpha, we have chosen our grid and we have chosen our delta x and delta y. The question is how to determine the delta t, the time step. There we can do a von Neumann stability analysis, assuming periodic boundary conditions in x and y directions. Von Neumann stability analysis. It is similar as we have done in one dimension. Again, we make the assumption that we have periodic boundary conditions, this acronym boundary conditions, in x and y directions. That yields following. I do not do the details, that is not part of this course, but of the follow-up course, TP 4165, Computational Heat and Fluid Flow. result is the following. Let's see, where are we in the numbering? 12. We have a stability condition that is similar to that we would have for the 2D diffusion equation. This indicates that we need diffusion. So alpha must be larger than 0. Alpha 0, pure advection is not possible. For that pure advection, alpha 0, the scheme is unstable. And the other condition is the following. It is this current number squared divided by the von Neumann number plus the C2 squared divided by the von Neumann number has to be smaller equal than 2. So these conditions. So let's see, we can normal stability analysis in per yields. I can add here the stability condition, that is the stability condition of the forward time-centered space scheme. And if we write what this means, then we can express that also in a different way. So these conditions correspond 12, or conditions 12 corresponds to the following. The first one, if we write out what this means, see here the sum of R1 and R2, we factorize the delta T, then we see that we should have the following. Clear that we should have a times that larger than 0. It has to be smaller equal than 1, 2 alpha, and then we have here the 1 over delta x squared and 1 over delta y squared. So that is then one condition that is coming from the first one. And we should have this condition satisfied, and if we write out what this ratio of current number squared and von Neumann number means, we find out that this is the Cell-Peclet number. So we know that as 13b, and that means that the ratio C1 over delta x divided by alpha, and so that is this term here, corresponding one in the y direction is the C2, that is the advection velocity in the y direction, but this sum has to be smaller or equal than 2. And this term here is the acronym is the Cell-Peclet number. So that is the definition, and that is the definition of the Cell-Peclet number in the y direction. So this is then equivalent to saying that the sum of the Peclet numbers should be smaller or equal than 2. So then we have these two conditions, and these conditions are necessary and sufficient for stability. In here, what we have introduced here by this is the Cell-Peclet numbers, where P delta y are the Cell-Peclet numbers. Again, in x and y directions. That is what we have observed for the one-dimensional diffusion equation. There we had also a condition that the cell-Peckley number for this scheme had to be smaller or equal than 2. Let's see. No, that was wrong. We did not have that for this. We had it in another context. But here it is appearing again. If you have in one dimension, then we see here that the Peckley number in one dimension has to be small or equal to 2. Because for the diffusion equation, we don't have the C1 and the C2. So they would be 0. So it was not correct what I said. But here we have this condition. And again, I want to stress that the scheme is unstable for alpha equal to 0. You see, for alpha equal to 0, we would have here infinity that can never be smaller or equal than 2. So, and this condition, by the way, is independent of delta t. It is a ratio between the let's see, how can we characterize that? That is, if we characterize it with a convection, with the characteristic length scale of the grid spacing divided by the diffusion. So it's also a ratio of convection to diffusion, but based on the grid spacing. So they have to fulfill this condition. So if we have a too large delta x and delta y, this might not be satisfied. So then we need to refine the grid. We need to get a smaller delta x and a smaller delta y to get this satisfied. So that gives us a condition on delta x and delta y, not on delta t. The condition on delta t we get from the first of these two conditions. We get it from here. That is in fact the same condition as we have for the 2D diffusion equation. So again, let us note that. F forward time, centered space, scheme 9 is unstable for alpha equal to 0. Because then we cannot satisfy this condition. And if alpha is greater than 0, we have to choose the grid spacings delta x and delta y small enough that this condition is satisfied, and then we can choose the time step according to this condition. And if the C1 and C2 is equal to 0, current numbers or the direction velocity components, then this is the stability condition for the 2D diffusion equation. So 13a is stability condition for the two-dimensional heat equation or 2D diffusion equation. And that would be 14 would be the equation du dt is equal to diffusion coefficient alpha, second derivative of u with respect to x, second derivative of u with respect to y. So it should be 2 here. And the stability conditions that we have here we can easily extend that to higher dimensions, to 3 dimensions. If we have, for example, in 3D, we would have here to add a plus R3, defined with alpha delta t over delta z squared, and here we would have to add a C3 squared divided by R3. Correspondingly, we would have then here a 1 over delta z squared, and we would have here a C3 delta z over alpha. And for 1D it is very simple, you just, that would be 0, that would be 0. This would not appear in 1D, and this would not appear in 1D. Then we have the 1D conditions. So then we have the way how to choose the time step. But we need then this extra condition on the sum of the Serpecklin numbers, which is this. Okay. Well, another way of writing these conditions, or just this condition, is that we can do it in the following way. So the conditions that we have 12 and 13 can also be expressed as so what we need is always alpha positive. We need always alpha positive. We have diffusion present that is needed, and that is the point I want to make here, that we can multiply everything, let's see, by that. R1 plus R2. This is clear. 2 R1 R2. And this here. Let's see. If we multiply that by R1 plus R2, we can multiply this by the sum of R1 and R2. I think the condition what I had in mind is the following. The following divided as the C squared plus the C2 squared smaller equal than 2 R1 plus R2 smaller equal than 1. That is the one I had in mind. This one is clear. Multiplied by 2. Then this one is clear. I'm now a little bit hesitating about this one here. Divide by R1 plus R2. That is not just the same, because then we would have R1 plus R2 and R1 plus R2 here. Let's see. It is not quite the same. No. You see, if we divide this by R1 plus R2, we would have then C1 squared divided by R1 plus R2. And we can argue the following way. C2 R1 plus R2. But we can argue the following way. If this is So this is something positive, and if we have something smaller, then we can do this trick here. R1 plus this R2. So we can use this. So the condition here is a little bit tougher than this condition. But if we have this satisfied, then this is satisfied by this argument here. Here we have something large, we have something smaller, the denominator, then we can estimate, do this, estimation, and then things are okay. So this condition is a little bit tougher than the one that we have in 13b or on this one. But if it's satisfied, it's okay. So that is one way to do the discretization, and the example that I showed you before, that was actually from this, using this scheme. So we can look at it again. Here I had a choice where the cell Peckley number was satisfied. Let's see my condition. So we are in 1D. Then the condition is, let's see, where do we have that? Oh, I took it off. Would be the current number. Let's see, would be the current number. I call that CFL squared plus 2 times the von Neumann number. Okay, it was a little bit too large actually. Okay, but I have used this condition here. I have not used this condition that we have here, which is a little bit tougher. So, but I want to show you another thing, and that is when when we violate the condition on the Peckley number. So we violate it now in the way that we reduce the number of grid points and thereby increase in that case, the delta x. So then we will violate this condition here. So we save that, and then we run it again. So now we have just we have fewer points, and you see what happens. We get an indication of an instability because we have now violated this condition of the Peckley number, so that the Peckley number should be smaller or equal than 2. Let's see, we can check that one the following way. We can look at the CFL number. That is my acronym here for the current number. That is to the power 2 divided, no, that is, as it's right, divided by the von Neumann number. You see it is 2.5. It should at most be, for being stable, 2. So this condition is violated, and the result of that is that we get an instability. With the one that we had before, we can do that again. Let's see. We can do that again, that we had already done. Run that now again. That is now with 80 points. 80 of 80 points, so that's 80 plus 1 together. So that is then behaving in a stable way. Let us check now the Peckley number for that one. So that is clearly lower than 2. So then that is okay. So here you see an example of when, in that case, the condition 13b on the Peckley number was violated with a smaller grid spacing. But this, with this grid spacing, with NJ80 for this example, we have the condition fulfilled. So that means that we have to choose a small grid spacing just to be able to have this condition, the second condition for stability on the cell Peckley number to fulfill. However, there is an alternative to this scheme, and that is the upward scheme. Then we have to decide, based on C1 and C2, how we do the discretization. That tells us where the upwind direction is. We can do that. It is similar to saying that we take the upwind scheme for the advection part and the centered scheme for the diffusion part. And the time discretization is then by explicit Euler method. So that is then the second scheme that we see is the explicit upwind method for advection and the explicit centered method for diffusion. Then we get the following scheme. So we can again say what we do. This is just what we have already in the title, advection with first order upwind method. That is the same that we have seen for the linear advection equation. So the advection velocity component C1 and C2 decide which direction is upwind, and in that direction we take the difference. And three ingredients: diffusion, with second order centered method, and the time discretization by first order explicit Euler method. In time. All this together gives them this scheme, and that is then 16. Time derivative is approximated in the way as we have already seen. It is the approximation of the u minus the O time level at grid point xi, yj divided by the time step. And now we have to make a decision depending on C1. We assume now that C1 and C2 in fact are positive. Then the upwind direction is in the x direction I minus 1. I minus 1, j, everything at the old time level, divided by delta x. Then for C2, the advection velocity component in y direction, we assume also that that is positive. Then the upwind direction is the uij minus 1. That is divided by delta y. And the right-hand side is the same as we had for the forward time-centered space scheme, the usual second derivative approximation of the x and y derivatives. Everything at the old time level. Of course, we are using the explicit Euler method. here, that is important, we have assumed that the C1 and the C2 are positive. Because if they are not, then we have to choose accordingly the upwind direction in a different way. So that is important. What we have done here is for C1 greater than 0 and C2 greater than 0. What can we say about the truncation error? Truncation error we can say by what we have in the different ingredients of the method. Since the method is using the explicit Euler method, it's only first order in time, like the FDCS. Regarding space, this is second order, and this is first order. So the lowest order decides, so only first order in space, in X and same in Y. So it means the method is first order in time and space. So it has lower order in space than the forward time-centered space scheme. And the stability condition, that turns out to be the following. It turns out that we have, if we have the general case, C1 could be positive or negative. In our case it is positive. But I generalize that we have the current number modulus for the x direction and the y direction. And we have then to consider 2 times the von Neumann number, sum of R1 and R2, and that has to be smaller or equal than 1. So that is the stability condition. And that is, compare that with the stability condition for the forward time-centered space scheme, that is number 15. So then you see we have now not this condition any longer. We have now a condition where both the convection and the diffusion enter. We have no condition in the Self-Beckley number. So this works for any Self-Beckley number. It doesn't say that it's good, but it's stable. So the accuracy is another story. So just quickly to get that, I call that scheme forward time, advection upwind, diffusion centered for the discontinuity. So we have the same problem, just another scheme, the same number of grid points, 80 in this example, and we see what is happening. So it looks very similar, but it turns out that, oops, that was not so good. It was the wrong thing. Let's see. So let's see. Take it again. So same problem as before, but now instead of forward time-centered space, this scheme, advection upwind, diffusion centered. So we get a similar behavior, but it turns out that this amplitude is much lower actually. The other one was around here, this is around here. So it turns out, I did a grid refinement to see where it should be. It should be somewhere in between. But nevertheless, the forward time-centered space scheme is more accurate. But this is more diffusive. But it has no restriction regarding the Self-Beckley number. Okay, so when we do the simulation for convection diffusion, we have to be careful about that, and that was the remark that we heard from Espen before, where is regarding the numerical viscosity. So here we have really quite some numerical viscosity. So therefore we need a fine grid here to get the accuracy good and to get the error low. But we have no problem with stability as long as this condition is satisfied. Okay, tomorrow we'll finish up this and we have a look at the scheme that is inside the solar algorithm for the discretization of the two-dimensional incompressible Navier-Stokes equation. It will give you a glimpse of that